This program is brought to you by Stanford University. Please visit us at stanford.edu.
You can now have this in the back of your mind all semester. What is it about this class that has changed you or changed the way you look at knowledge or yourself or your life or the physical world around you or whatever? So that's going to be one of the questions on the final. So you're already halfway to your A, right? Here's that website that I mentioned before. Take a look. They've got a top 10 list for astrobiology stories in 2007. There will no doubt be lots of great ones in 2008. I think this is going to be a much more upbeat year than last year. It's going to be great fun. So you should feel free to ask questions. And without further ado, I'm going to pass you over to Seth Shostak, who is, what's your official title? Senior astronomer at the SETI Institute, Search for Extraterrestrial Intelligence in Mountain View, and he is one of the, you've probably seen him on television anyway, and he's just one of the most amazing people you're going to meet. Seth?
Thank you, Lynn, and I always tell audiences not to applaud before the talk. You'll only regret it. Okay. By the way, those cavemen out there,
Yeah.
They are out there, actually. They're called Klingons. Yeah, right. Also, I noticed you have Dave Morrison coming on February 5th, is it?
Yeah.
Something like that. Well, you may have been reading in the papers that there may be a collision of an asteroid with Mars just a few days before that. Only has a 4% possibility of happening. But everybody here is hoping that this rock actually does slam into Mars, because it'll be very interesting for the astrobiologists if it digs up a big crater and they can see if there's any water at the bottom or whatever, that kind of thing. So you can hope. It's kind of a schadenfreude, you know. It's okay if the rocks hit somebody else's plant. This rock, by the way, if it were to hit Palo Alto, would obliterate it. Instant urban renewal, which would be good news for Menlo Park. Okay. I'm going to talk to you a little bit about cosmology. And cosmology may be the oldest discipline in astronomy. Cosmology, what does it mean? It just comes from the Greek cosmos, which I think just means essentially everything, the whole universe. Everything you can possibly see or experience or measure or whatever, that's the cosmos. And cosmology is just, well, what is it? Now, you're all sitting there thinking, oh, well, there's the Big Bang and this, that, and the other. But the facts are that you're really the first generation to have any decent idea of what the cosmos is like. And even your idea, it turns out, is not so good. This is sort of a view of what the universe was like. I don't know how old this is, but it's a couple hundred years, 400 or 500 years old. And you can see here's, lovely Milpitas. And this guy here who's trying to figure out what the universe is really like, how it really works, right, is somehow peeking through the vault of the heavens, and he sees some clockwork and stuff like that back then. They were just beginning with gears, and Newton was on the scene, and so forth and so on. So they figured that the universe was some sort of giant clock. Okay, well, this is a nice view. It's a little better than the view they had a couple of thousand years earlier. This is about 500 BC or whatever. The Greeks, and their view of the universe was really simple. There was, the Mediterranean and a few places that were habitable by Greeks, and then there were these steep cliffs. I don't know where they got all the detail here. There's a lot of data there. It's a little unclear, but that was it. It was all floating in a big bowl, right, somewhere. Okay? Now, this clearly would have been a great time to be a cosmologist, because you could make really radical discoveries about cosmology. All you had to do was, for example, walk to the east or west. It really didn't matter, right? Cross the Mediterranean, walk down through the Atlas Mountains of North Africa, whatever, and see if you actually fall off a cliff if you come to this big ocean, right? I mean, there are a lot of cosmologies like that. You probably heard about the one, and I always forget which culture it was that had this. I think it was Indian, but maybe wrong, in which the Earth was just a ball sitting on top of a turtle, right? And then, of course, the question always arises, yeah, but what's the turtle on? Well, that's on another turtle. But then the question is, what about that turtle? And the usual response is, look, it's turtles all the way down. Whatever that means. But you see, with a cosmology like that, I mean, one of the nice things about astronomy, it's a very old discipline, as you know. It's considered to be the oldest of the sciences, although math probably is older. But in any case, it's a science that for a long time didn't have any way to really measure anything except to look at it, right? And until 1609, maybe you had to look at it with your eye. You didn't have anything better than that, right? Telescope was first used in 1609, 1610 by Galileo. So For a long time, astronomy was just looking up at the sky and seeing how things moved around and trying to discern whether there was anything to it, whether there were any patterns, whether there was anything to be learned by it. But it developed this attitude that if you had an idea about how the universe was put together, that was fine, but it didn't mean a thing unless you had that swing. It didn't mean a thing unless you could prove it by observation. That's still true with astronomy. People come up with ideas about, well, the whole universe is a giant black hole, or maybe our solar system is just an atom in something else, or whatever. People have they send me emails every day with these crazy ideas. In the end, I mean, I just call them crazy because it makes it easier to answer the email. Maybe some of them are right. I mean, I don't know. But the point is that for astronomers, look, you can have any idea you want. I don't care if you're a theoretician at Stanford, but if it doesn't predict something I can see with my telescopes or with my eye or some other measuring device, then it's not worth very much. Okay, so if you had a cosmology like this, you could obviously disprove it. If you had the turtle cosmology, all you have to do is sail to the southern hemisphere, look up in the sky, and see if you see turtle shell everywhere, right? And some of you have been to the southern hemisphere, and you know that there is no turtle shell there, so you can dispense with that. This was the cosmology that had the longest run of any of them, right? This was the old Copernican model, right, where the universe the universe back in those days consisted of essentially the solar system. At least they got away from the Greek idea that it just consisted of the Mediterranean. You had the Earth in the middle, of course, because that's where you live. And then the moon went around that, and then Mercury and Venus, and the sun went around just outside of Venus. Let's explain why it's so hot on Venus. And then Mars and Jupiter and Saturn, and that was the end of the planets, right, because they didn't have telescopes, of course. And then outside of that, they had the stars that were just sort of a backdrop. Okay, and that's what it was. And this is what people believed for thousands of years, right? Okay, now, this sort of cosmology actually did predict things. I mean, you could use it depending on how fast these things rotated around. They were on big crystalline spheres, right, that God had made somehow and put these bright lights on them, because they couldn't see them as disks. They were just bright lights, and moved them around. And if there was some regularity to that, maybe you could predict where Mars was going to be the next night or the next week, or Jupiter and things like that. And they developed very, very elaborate systems, in fact, based on this cosmology to predict the positions of the planets and the sun and the moon, which were the things that moved relative to the background stars. And they worked pretty well, actually. Believe it or not, they worked pretty well. They didn't work perfectly well, but they worked well enough. And in fact, when this was all overthrown by Copernicus in about 1450, the new system that he introduced didn't work as well, right, in terms of predictions. It took a while before they refined that system. So it wasn't that Copernicus said, look, I got a better scheme here that'll do better at predicting where Jupiter's going to be 3 months from now. It didn't, in fact, but anyhow, it was a better scheme because it was closer to the truth. Is this correct? All of these ideas went away, in fact, beginning in around the 1500s, when people started measuring the positions of, in particular, the planets, the sun and the moon, very accurately. No telescopes. They just had, giant, essentially, protractors that were sort of aimed at the sky. This is Tycho Brahe. This is his day job, well, night job, actually, to measure the positions of things in the sky. That's right. He was a Dane who, kind of an interesting guy because he had a zinc nose, or maybe it was copper. He'd been in a duel, somebody sliced off his nose. But he was actually remembered not because of that metallic nose, but for all these measurements, which led, in fact, to Copernicus and Newton's revolution in how the solar system worked. Well, all right, enough of all that. I give you this history only because it's good for what's left of your souls. In this century, in the last, actually, 2 centuries, the question has become somewhat different, because beginning in the 1900s, the 1800s, the 19th century, beginning in the 1800s, we were able to measure how far away the stars were. Now, that sounds like a fairly trivial statement. Oh, the stars, how far away are they? Because you can just read about it in a textbook now. But imagine you're born in, 1800, and somebody says to you, well, Marvin, you see that star up there? How far away is it? Right? How would you figure that out? How would you figure out how far away it is? Right? With the planets, you could do a little bit of geometry. You could see, well, all right, this is where it is now, and in 6 months from now, the Earth is on the other side of its orbit, and I know more or less how far it is to the sun, and I'll do a little bit of high school geometry and figure out how far away the planets are. And they could do that. But the stars are so far away, high school geometry doesn't really work. Not with the kind of instruments they had in the 19th century, anyway. So how did they do it? Well, they had to build better instruments. That's how they did it at first. They said, we'll still use high school geometry. We'll build better instruments. And a guy by the name of Friedrich Bessel in probably get this date wrong, I think it was 58, or maybe it was 38. Anyhow, somewhere about mid-19th century measured the distance to a nearby star. Okay? And in fact, the distance to this star was about 11 light years. Do you all know what a light year is? Anybody doesn't know what a light year is? Anybody want to hear what a light year is? Okay, you all know what a light year is. Either that or you're just shy. Okay. But a light year's a long way. A light year is like almost 6 trillion miles. About what I have on my Honda. Okay. So this was 11 times that, right? That's a long way. And this depressed everyone because they realized, hey, we've been sitting here worrying about this solar system and that sort of cosmology. In fact, the universe is far, far larger than we thought. And this was one of the nearest stars. This was one of the nearest half-dozen stars, 11 light years away. The nearest star turns out to be about half that distance. Okay. So suddenly the universe opened up. Blaise Pascal wrote something about these enormous spaces terrify me and so forth. We realized the universe was huge. Well, it got much huger. Now, it turns out that you can learn something about cosmology by doing a really simple experiment, namely going out at night and seeing, if you can raise this, no, you can't. All right, I'll draw it over here. Here's the experiment. The experiment is, what is it about the nighttime that's different than the daytime? Answer is, it's dark. Now, that might sound trivial as well, but it's not so trivial, because it tells you something rather interesting about the universe. This very simple observation. Suppose, here you are, here's Earth, and there's your eyeball, whatever. Okay, there's your eyeball. And you're looking out, and maybe in this direction there's a star. So a star, whatever it is, it's something that puts out light, right? Okay, and if there are a couple of stars around, of course, you look in this direction, you don't see any stars, so that's dark. You look in this direction, maybe, and you see this star, and that's light. And okay, that explains everything. The fact that the night sky is dark, however, says something about this picture. Because imagine that the universe was infinite. Right? We don't know whether it's infinite or not, by the way, but it could be. And that seemed to make sense to a lot of people. They said, look, the universe probably goes on forever. Because if it doesn't, there must be some place that you get to where it's, where there's a sign that says, last gasp before the end of the universe. And a lot of people had a sort of a philosophical problem with that. Right? They didn't like the idea that God would have made something that had sort of a brick wall. Here's the end. Right? Okay, so imagine that these stars go on forever. So there's one over here, one over there, one over there. If they go on forever, you can see that no matter which direction I look at, there's a direction there. It should be a straight line. Sooner or later, it's going to hit a star. Right? If they go on forever, for sure, it's going to hit a star. No matter what direction I look at, sooner or later I'm going to hit a star. And that means that the whole night sky ought to be as bright as a little pinpoint star. Right? The whole sky should be the same surface brightness as the sun. The whole sky should be lit up like suns everywhere. Okay? Think about that. Well, as I say, you can go out tonight, although it's a bit cloudy, but nonetheless, you'll notice that it will get dark. So this is not true. This is called Olber's paradox, because Olber was the guy who pointed this out. In fact, he wasn't even the first guy who pointed it out, but he got the credit, a frequent story in astronomy. Now, how could you beat this rap? How could you, in fact, have a night sky without having the universe be infinite? Or having the universe be infinite. Without having the universe be infinite, it's obvious. I mean, these stars end, and of course, depending on where they end, you might just have lots of dark. But could you have an infinite universe and still have a dark sky? Well, there was a way to do that, it turns out. If the universe is expanding, then you'll have a dark sky, even if it's infinite. Because the stars that are farther away, they're moving away from you. And when they move away from you, their color changes. There's something called a Doppler shift. You all know about the Doppler shift? You go down by Caltrain, the train coming toward you has a higher pitched whistle than when it's moving away from you. Right? It never goes the other way. It never goes as it goes by. Right? Because when it's coming toward you, the waves kind of bunch up, the sound waves, and when it's moving away from you, they're kind of stretched out. It's just the motion of the train. Well, the same with light from the stars. When they're moving away from you, the light gets stretched out, which means it gets redder. And if it gets stretched out enough, it gets infrared, and then it gets even, radio waves, whatever, and you don't see them anymore. So by having the universe expand, you can account for the fact that the sky is dark at night. So either the universe is finite, or it's expanding. And the only data you need is the trivial observation that the night sky is dark. Nobody made this conclusion. Actually, they did. And I mean, people realized that there must be something going on. At first they said, well, maybe it's just dust between the stars. That doesn't work because the dust would always heat up to the temperature of the stars sooner or later. They figured that the universe was, in fact, finite. And 100 years ago, 1908, if you had asked astronomers, not some guy off the streets of Palo Alto, but if you'd ask astronomers, what is the cosmology of the universe, they would have said, well, it consists of a big ball of stars. We'll call it the Milky Way galaxy because we always have. Right, a big ball of stars, but that's it. And outside that, there's nothing. That was the picture. Only 100 years ago. Okay. Now that picture became a problem when people began to study things like this. This is just a picture of the night sky. It's a negative print because that's what astronomers tend to look at. It's a little easier to see faint stuff. So the sky's white and the stars are dark. But you see this smudge here. Right? They were called nebulae because astronomers are very good at naming things. For example, telescopes. The 140-foot diameter radio telescope in Greenback, West Virginia is named the 140-foot telescope. Right? The 300-foot telescope was called the 300-foot. These things are called nebulae, which is just Latin for cloud. Right? That's right. Just smear. Right? Just some sort of fuzzy thing. Okay. I don't want to say astronomers are unimaginative, but try going to a party with 100 of them. Okay, so the question was, what were these things, these smears? Because people could see these things. They could see these things in the 1700s, even the crummy telescopes they had back then. They could see these things, right? And the question was, well, is it some sort of, they knew there was plenty of dust and gas out there amongst the stars. Maybe it's just more gas and dust. And maybe this is gas and dust that's forming a star, or maybe making planets, or who knows what. But there were other people who said, no, wait a minute. This is not, all these stars here, they're just in the Milky Way. They're nearby, they're buddies. But maybe this is something really far away. Maybe this picture is like looking through a backdoor screen, right? A screen door, where you got all the screen here, but that's something really far away, way beyond your house. That possibility is certainly there. I mean, you can't tell by just looking at this picture. In order to tell whether that's true or not, you have to be able to measure the distance to one of these nebulae. And that was the big triumph of the 20th century, the early 20th century, that people figured out how to measure the distances to things that turned out to be very, very far away. Okay, now how do you do it? Well, I mean, you think of a lot of schemes, and people have thought of a lot of schemes, and a lot of papers have been written, and various people have become, famous amongst a group of people that are no fun at a party by having thought of ideas. But really what you want to do is find one of these in space, a standard candle. Standard candle. All it means is something in space that you know how bright it is. Because, for example, if I had a 100-watt light bulb, all 100-watt light bulbs, all the incandescent ones, are about the same brightness, right? You can buy Philips, you can buy General Electric, but they're always, 100-watt light bulb puts out the same amount of light, pretty much irrespective of the brand. So you can imagine buying a 100-watt light bulb and putting it over there on the table, and you stand over here with your light meter, and you got one from an old camera, whatever. You measure the amount of light. Then you move the thing twice as far away. You measure the amount of light. Obviously, the amount of light goes down. By how much? Yeah, the inverse square law. So it goes down by a factor of 4. It doesn't go down by a factor of 2. It goes down by a factor of 4. But anyhow, that's freshman physics, and if you haven't had that, it doesn't matter too much. All it is that it goes down by a predictable amount. You move it farther away, it keeps going down. So you could turn this whole experiment around, have a buddy with that 100-watt light bulb somewhere here on campus at night, and they're down there somewhere, and you measure the light, and you can tell how far away the light bulb is just on the basis of this brightness. But in order to do that, obviously you need the light meter. That's not so much a problem. But you need to know that it's a 100-watt light bulb, and that he hasn't switched it out with a 500-watt light bulb or a 10-watt light bulb, right? Standard candle. In other words, something that puts out a standard amount of light. Well, astronomers were looking for things that might be standard candles that they could use to measure these things. And they say, well, if they're very far away, maybe there's stars in there. Maybe there's some big bright stars that are always the same bright. And it turned out that there were. Some big bright stars known as Cepheid variables, right? Cepheid, because the first one was found in the constellation of Cepheus. Sounds like a head, but I think it's some sort of marine mammal. Anyhow, these have been studied, in fact, by a woman down in South Africa. She was working for the Harvard College Observatory, Henrietta Leavitt. And not many people have heard of her because she did this work in the early part of the 20th century, and it was great work, but it was done by a woman, and of course, you know, it didn't get the notice that it should have, because she, in fact, provided the whole key for figuring out how to determine the distances to these galaxies. She was able to say, hey, look, these guys are not only bright stars, which means you can see them even in smudges like this that might be very far away, but they were unstable. Right? Now, that doesn't mean that they blew up at their spouse every couple of weeks. What that meant was that they would get brighter and dimmer, and then they get brighter and dimmer, and they get brighter and dimmer. Well, okay, you know, stars kind of pulsate. If they're unstable, if they're a little bit too big, and, you know, their gravity is fighting the radiation pressure from their nuclear engines, whatever. They're doing this sort of thing, so they get brighter, then they get dimmer, and they get brighter and dimmer. But you found that the bigger ones got brighter and dimmer slowly. It took a week or so. And the smaller ones, the ones that weren't quite so bright, got brighter and dimmer much more quickly. She was able to figure that out because she was looking at some nearby group of stars. It was called the Magellanic Clouds, but that doesn't matter, although you might want to use it at your next cocktail party. She was looking at a whole bunch of them, and she knew they were all more or less at the same distance, and she could establish the fact that if you plotted here their brightness versus their period, how long it took for them to go through one cycle of going bright and dim. Well, if they were dim, their periods were rather short. They, you know, only took a day or so. And if they were really bright, it took a long time, and she filled in that plot there. Now, you might say, okay, interesting technical paper, maybe we'll give her a degree or something. But this had profound implications because it meant that if you found one of these guys, all you had to do was sit around with a calendar or a watch and see how long it took to go through one cycle of getting bright and dim, and now you know how bright it is. See, it's sort of, now you know what wattage bulb it is. Well, Edwin Hubble realized this, and he found some Cepheid variables in nearby galaxies, in particular the Andromeda Galaxy, and he could figure out how far away they were by doing that. Okay. So everybody knows about Hubble, who was, by the way, not such a nice guy, but everybody seems to have forgotten about Henrietta Leavitt, who did the fundamental work here. But it turns out she wasn't so nice either, I'm told. Okay, let me cut to the chase. This is, never mind who it is. This is Hubble, who had this strange anatomical deformity out of his mouth. Okay, there he is, up close, closer than you'd want to get to him. And he made this little plot here. He made this plot in the late 1920s. Arguably the most important scientific discovery of the 20th century. And I know you're thinking it's the video game, but it wasn't. It was this. Right? What he did here, this is a plot. And I know every time you show a plot, you lose 10% of the students. Okay, now I've got 12 of these, so. All right. So what he has plotted here is some dots. These are these smudges, what later became known as galaxies. Right? But you know, just each one of those circles or dots is the measurement on a smudge. Right? And he was able to find some of these Cepheid variables in these smudges, so he could figure out how far away they are. So this is the distance scale. Nearby, far away. Plotted on the vertical axis was how fast they were moving, either toward us or away from us. And that data, of course, most of it Hubble got himself, but there were some other astronomers involved. It was just a matter of seeing whether the light was, you know, a little bluer or a little redder, just using that old Doppler shift, the Caltrain trick, to figure out, well, is it coming toward us or is it moving away from us? You might think, what does that have to do with anything else? Well, it clearly has something to do with everything else, because even though these data are kind of crummy, you can see that Hubble has been daring enough to draw a straight line through it that says the farther away one of these smudges is, the faster it's moving with respect to us. And in fact, they're all moving away from us. I mean, with the exception of a couple of guys down here. They're all moving away. All these smudges are moving away from us. It's as if we have bad breath. They're all moving away, okay? And the farther away they are, the faster they're moving away from us. Okay, well, this is the expanding universe. This is like if somebody were to be, you know, uncharitable enough to come into the class here and pull the pin on a hand grenade in the middle of the class, right, in the middle of the room, and you looked at this situation a fraction of a second later, you see all these bits of shrapnel flying away from the hand grenade, or where it was, and you'd also find that the pieces of shrapnel that were moving the fastest were the ones that were farthest from you, right? Exactly this. So it looked like the cosmos was blowing up. And this is a fundamentally new idea. I mean, Einstein had tripped across this in his equations of general relativity earlier in the century, but he didn't believe it himself because the astronomers kept telling him, look, Al, the universe is static. It's always the same. You can go out night after night, it isn't going to change much. Oh, well, a star will get born here and the star will die there, but you know, the whole thing doesn't change. That was wrong. It was blown up. Now that per se is really an interesting thing to learn, but clearly if you think for another 5 seconds, you realize, well, look. So we got this situation where the universe is expanding. Why don't I run that movie backwards in my mind? Because if I do, there must be some point where all the pieces come together, and I just have to do a really little bit of math here, and I can figure out when the pin was pulled. Right? And he did that, and it turned out that the pin was pulled, according to that, a couple of billion years ago, which was distressing because even in those days they thought there were stars that were older than a couple of billion years. Right? Even the sun is older than a couple of billion years. So there was something wrong there. But what was wrong was that some of these measurements weren't quite up to snuff. Okay? But the point is that clearly there must have been some beginning to this. And that's so ingrained now that you don't think that that's a problem. But a lot of people thought it was a problem, even in the 1940s. The late 1940s, Fred Hoyle, a famous British theoretician, was being interviewed by BBC about this idea that the universe had a beginning. And Fred, a very clever guy, did a lot of good work, bonkers on some other things, which Lynn will probably tell you about later in the course. He said, look, the idea that the universe began with some sort of big bang is ludicrous, right? He was trying to make fun of this idea by calling it a big bang. Unfortunately for Fred, the BBC audience really liked that term, and now everybody calls it the Big Bang. Yes, sir?
Is the current age of the universe still based on a version of the Goldilocks?
Yeah.
And it's just a better measurement of it?
Yeah. The question is a good one. He's asking our current estimate of the age of the universe, and Lynn let that trip here. I don't know if any of you picked up on it. 13.7 billion years. Is that based on, essentially doing this trick and running all the velocities backward? And the answer is no. It's not. It's not. It's based actually on a theoretical analysis of the cosmic background irregularities. Yes, it's much more difficult now, but it's also much better. I have to say that I had several girlfriends who earned a very modest living trying to do this and run the clock backwards and figure out, do this plot better.
Seth, would this be a good time to take?
This would be a great time to take a break.
Okay. What we're going to do is just give yourself 2 or 3 minutes just to stretch your legs, get over
Stretch your universe.
what's known as butt fatigue, and we will reconvene. While I'm thinking of it, there is a textbook for the class, written, interestingly enough, by Seth Shostak, and I'm sure if you bring in a large bribe at the last class, he'd be happy to autograph it for you.
Even a small one.
Even a small one, he said he would be willing to take because he's an astronomer. And the bookstore, I think, screwed up. I emailed them the other day, so there may not be copies there yet. And there will be a syllabus online that has chapters, and a lot of the people who come into lecture will give you outside reading. And since there's a range of ages and experience, there'll be a lot that'll be optional just for if you're particularly interested in a single lecture. So why don't you just stretch for a second, and let's turn Seth back on.
Nice. Okay, so here it is. Here it is, the history of the universe as we knew it in 1929, and still more or less know it. Okay, it was some sort of big bang, right? Things blow up, you get gas everywhere. But of course, because in these earliest moments, the universe is very small, but there is something called the uncertainty principle, Heisenberg uncertainty principle. There are other uncertainty principles, such as when you're going to get your order at Denny's. But the Heisenberg uncertainty principle here means that the universe wasn't completely uniform, even in those early days. It was very small and very hot and very dense. Right? Typical temperatures there in the first moments of the Big Bang, well in excess of 10 to the 30th degrees. And you may wonder whether that's centigrade or Kelvin, but at 10 to the 30, what do you care? Right? I mean, obviously things are different, but they're slightly inhomogeneous, and that means that by the time the universe blows up to something a little more reasonable after a few tens of millions of years, They're clumps. And then the clumps can collapse under their own weight to form galaxies of stars, which when they form, often, maybe almost always, will make planets, and then you'll get a little bit of dirty chemistry, and then you'll get, this course. Okay, so there's the picture, and all it took was 13.7 billion years, and there's Carl Sagan's, oh, never mind what Carl Sagan said. Okay, so that was the story. Now, this...
Sorry, Seth. Is there anyone here who's never heard of Carl Sagan? It always upsets me when you start looking younger and younger in this class.
Who hasn't heard of Carl Sagan? You can, go ahead, tell me. Right, I think it's a good thing myself.
And the ones who haven't laughed.
All right. All right, well, ask the person sitting next to you. Let them berate you for a while. Now, this story has been elaborated in many ways, and in particular, what's really interesting are questions about what went on here at the beginning, because everybody sort of wants to know, well, who pulled the pin, right? Is that a question that astronomers or physicists can answer, or is that something only the theologians can approach? That kind of question. And, of course, what happened here at the beginning, and then there are other problems. I'll give you a sample of some of the other problems. If you look with a big telescope at galaxies, for example, in that direction tonight, right? And you make a picture, and it looks like all the other pictures you've seen, with galaxies everywhere and so forth. And those galaxies, how far away can they be? Well, they could be 10 billion light years away. We can easily see galaxies 10 billion light years away. We can actually even see some galaxies that are 12 billion light years away. We can't see any galaxies that are 14 billion light years away. Why? The universe is only 13.7 billion years old, right? That's when this thing went off. T minus 13.7 billion years. So clearly, anything that's 14 billion light years away, there might be stuff out there, but the light hasn't had enough time to get to you yet, right? You don't know yet. All right, but you can see galaxies 10 billion light years away, so you make this photo and you see them all scattered across the photo. Then you turn the telescope 180 degrees and you make a picture of the deep sky in that direction, and you get the picture looks pretty much the same. Gosh, Marge, it's hardly any different that direction. Oh yeah, the individual galaxies are in different places, but it isn't that there's something radically different over here than over there. The universe looks pretty much the same no matter what direction you look at it. Okay? And that actually is like the Ober's paradox. There's something very profound about that. Because how do those galaxies know to be sort of arranged in terms of size and distribution as these guys over here? Because these guys are 10 billion light years that way. Those guys are 10 billion light years that way. The distance between them is 20 billion light years. The universe is only 13.7 billion light years old. Those guys haven't had a chance to talk to those guys and get their act together. Right? It's sort of like you go to a party and everybody's wearing the same thing. And somebody had to make some phone calls. Right? It's not going to happen by random chance. Right? They need to be able to communicate. Well, it was problems like this that have led to a lot of research and occasional tenured positions at MIT and so forth, for people who think about how you can beat that rap. And the way you beat that rap, we may get to, we may not. Okay, here's Andromeda gas. Let me say a little bit about the Big Bang too, because if you're new to this idea, there are a lot of interesting questions, such as the fact that the galaxies are all moving away from us. Does that mean we're in the center? Right, it would with a hand grenade. If all the pieces of shrapnel are moving away from you, you must be where the hand grenade pin was pulled, right? Because if you're over here, maybe some things are coming toward you. Rather unfortunate, but okay. But nothing's coming toward us, with the exception of some very nearby galaxies that really don't count, right? So everything's moving away from you. Does that mean we're in the center? That would be a wonderful thing. That would mean, as you probably already think, you're the most important thing in the cosmos, right? Because everything else is centered on you. Well, it doesn't mean that. And the way to think of it, there's a lot of ways to think of it. Probably the best way to think of it is what's called the old raisin pudding analogy. Right? Imagine you're making a bread pudding, raisin pudding, whatever. Right? So you get this big bowl of batter, and you throw a whole bunch of raisins in it, and then you throw the thing into the oven. Right? Now imagine that those raisins are galaxies. Okay, so you're sitting on one of these raisins, and you're looking at the other raisins, and as the heat goes on, the whole thing expands. Every other raisin moves away from you. It doesn't matter what raisin you're on, that picture is the same. All the other raisins are moving away from you. Doesn't mean I'm top dog raisin, I'm the center raisin in this cake. It's not true. It'll be true for all of them. In fact, that's a principle of modern cosmology. Any theory that says that you're special is probably wrong. Okay. People are very skeptical about that. But that's one thing. Right? let's see, what are the other things that people always ask about? Oh yeah, the other view of the Big Bang is that it happened in a big, dark, empty space, right? That there was this big nothingness, 13.7 billion years ago plus 1 second. There was nothing, and then suddenly, somehow, bam, this thing goes off and starts filling up this space with this junk, which eventually became, you know, the galaxies and you, right? Well, that's wrong, because space is part of the universe too. There was no space. There was no empty room. That was created as the universe expanded. In other words, back in that first little dot there, the whole universe was the size of, in the beginning, you know, just a pinprick or an atom, depending on when you're talking about. And after a tiny fraction of a second, it, you know, swells up to a grapefruit size, and then to the size of the solar system, and then begins expanding the way it is now. Right? But there was no outside that. There was no space on the outside where you could look at this whole thing exploding and say, well, it looks like a pretty good job. Right? The other question that I used to get this from my niece until she went into art, but her question was always, well, Seth, 13.7 billion years ago, the Big Bang goes off. What was there before the Big Bang? Okay. Now that's actually a good question. I used to dismiss it when she was 11 years old by saying, look, Becca, that question is not legit. Because just in the same way that space came with the Big Bang, the same is true of time. Right? Time is a property of the universe. So 13.7 billion years ago, time began, but before that there was no time, so you can't ask what was before the Big Bang, because the word before doesn't mean anything. And Becca would walk away from this response suitably disappointed. In fact, actually, in retrospect, maybe she was right and I was wrong. It was frequently the case, actually. Because, you know, actually astronomers and physicists are sort of asking that question too. I mean, does the universe just form like that? I mean, did God just do it? I mean, it's easy to say God just did it. Right? The trouble with that is that if you're a physicist, you can't write a paper for phys rev letters, you know, God did it. Right? You won't get it past the referees, right? So, you know, physicists are always looking for, well, maybe there's some other explanation. Maybe we can think of something else. Now, one thing about the universe, and it's kind of implicit in this whole course, is that, and it's rather disturbing actually, there are whole entire conferences devoted to this problem, that the universe seems particularly set up for life. May not strike you that way as a student, but it's true, right? What do I mean by that? Well, you know, if you take freshman physics, you learn about what the gravitational constant is and so forth and so on. It's just some number, right, that's printed in the book that people measure. But where'd that number come from? Well, it's just the way the universe is. Well, if you change that number a little bit, then maybe the whole cosmos would have exploded so fast that, you know, it would have never condensed into stars and galaxies and planets and you. If the constant had been a little, you know, different so that gravity was a little stronger, then you would have had the Big Bang and then a stop and then a big crunch. And once again, you wouldn't be suffering through this lecture, and you wouldn't be here. Right? So that's a little peculiar. How come it's just right? Sort of like Goldilocks, right? Just right. This is true for a lot of the atomic constants and so forth that make stars work. This was pointed out by Fred Hoyle. It was pointed out by a lot of people. And it seems to be that there are only a couple of ways around this problem. Right? One way around it is just to say, go back to God and say, God just made it that way, so you'd be here. Right? Okay, then you're done with that story. Another possibility is to say, well, the laws of physics just don't allow those numbers to be any different than they are. And you can say, well, what laws? And the answer is, we don't know, but, you know, the new generation of physicists which are sitting in this room will figure that out. That could be. It could be. It's an argument from ignorance, but maybe. A third possibility, and this is very trendy these days, and it's actually promoted by some of the physicists here in the Stanford physics department with great enthusiasm, is to say, look, here's the real answer. Universes are cheap. Right? If you add up all the energy in the universe, it turns out it's zero. Right? There's all this kinetic energy, there's all this potential energy. It turns out that as Alan Guth once said, the universe is the ultimate free lunch. It doesn't cost any energy. You can make a universe for free. In other words, our universe might just be the science fair project of a kid in another universe. Right? If there is such a thing as another universe, but maybe he's sitting in the other universe, he just twists time and space, right in a classroom, and bam, he makes a new universe. Right? Of course, it's not in his universe, so we can't really see it, but it starts up, and then 13.7 billion years later, you get, you know, what we have today, right? Well, if universes are free, the thought is, well, maybe universes are very common. Maybe they're just as common as cheap motels, that there are universes everywhere, right? And they're born with random properties because, you know, you make a universe and it's going to have some sort of property, but, you know, you can't predict. And most of them are crummy universes. They don't have 3 dimensions, 3 spatial dimensions. They only have 2. And everything's kind of flat and uninteresting. Or maybe they have 5 and that's not so good either. Or maybe they have 2 stronger gravitational constants, or maybe 2 weaker. You know, but if you make the number of universes people talk about, which is numbers like 10 to the 128th universes, that's a very big number. Right? If you make that many universes, then by chance, right, some of them are going to be okay. It's like if you buy 10 to the 128th lottery tickets, to begin with, you exhaust all the forests on Earth because printing all those tickets. But, you know, you're going to win. Right? Somebody's going to win. And then you just invoke, at that point, you just invoke what's called the Anthropic Principle, which just means man-centered. They never have a gynotropic principle, but the Anthropic Principle, which says that, of course, we're in the winning universe because if we weren't, we wouldn't be here, right? You like that? This universe is great because if it weren't, you wouldn't be here to say it's great. Okay. Anthropic Principle, sort of a simple version of it. Okay, so there's the argument. You hear about parallel universes. They talk a lot about parallel universes on late night radio and stuff like parallel universes. But this is why parallel universes are very sexy. You can try this again at your next cocktail party. You know, somebody comes up to you and you think, well, I want to impress them. Start talking about parallel universes. See how far you get. The reason that they are trendy is because they might offer a reasonable explanation for why our universe seems so nicely set up for life. The whole rest of this course is about life. Right? This dirty chemistry that seems a little more interesting than the rocks out here. Right? And it might only exist because we happen to be in one of the winning cosmos. Okay. Now, I'll just show you a few pictures here that sort of prove that the Big Bang maybe really happened. Here's some pictures from Hubble. These are pictures of galaxies, right? All those smudges turned out to be galaxies, big balls of stars, actually mostly disks. Well, half of them are balls and half of them are disks. Okay, big agglomerations of stars. Typically in a galaxy, you have a couple of 100 billion stars. And the number of galaxies that we can see with our telescopes is on the order of another 100 billion. You might multiply those 2 numbers together in your head. You've probably already done that, right? Or the back of the shirt of the guy in front of you. That's 10 to the 22 stars. Right? That's a 1 followed by 22 zeros. That's the number of stars in the visible universe. And you can make your own calculation. I figure that's about the number of grains of sand on all the beaches of America. Okay. That's a lot of stars. Okay. And mind you, that's not the end of it. I mean, if you could go to, the point is you can't see any galaxies that are more than 13.7 billion light years away. If you could go to the farthest galaxies and get there and look farther, you'd see more galaxies. And the question is, would you always see more galaxies, or is there, you know, some sort of end to the universe, either because it curves in on itself, or it's just finite, or what? We don't know the answer to that. But certainly within the visible universe, there's a lot of stuff. 10 to the 22 stars. So here's a galaxy nearby. By the way, yes, ma'am.
Can you explain what a galaxy is?
Yeah, I obviously haven't done a good job with it. Let me go back here. Here's a galaxy. Here's one. That's the Andromeda Galaxy. You can see this with your naked eye in the winter, actually. Or is it in the summer? More in the summer than in the winter. It just looks like a little fuzz ball. This is the one that Hubble first looked at. In fact, it has some buddy galaxies, these little guys here. But it's just a big city for stars, if you will. Right? Stars just don't exist everywhere. They're not like, if you will, grains of sand that you just throw up and they're everywhere. They tend to congregate. They tend to be in organized structures called galaxies. The word galaxy, of course, just comes from the Latin for milk, because, you know, the Milky Way, which is, by the way, our galaxy, you know, the stars in our galaxy, tend to pile up when you look along the edge. You know, look like milk to the ancients, so they call it the Milky Way. But this is somebody else's galaxy. Forget all these stars in the foreground. That's the screening, right? That's stuff in our galaxy. But there's, you know, in this galaxy has about 300 billion stars. Okay. And they're all, you know, there's just big flat spiral thing rotating around. This is one of about 100 billion galaxies we can see. Did that answer the question? Something else I probably should point out. People sort of wonder if this expanding universe, does that mean that some of the galaxies are expanding faster than the speed of light? Because everybody knows that Einstein's theory of general relativity says that, you know, matter can't go faster than the speed of light. It can't even go at the speed of light. So how could these galaxies be separating from one another faster than the speed of light? Well, the facts are that the galaxies are not moving through this empty room separating. What's happening in the Big Bang is that space itself is expanding. The pudding between the raisins is expanding. And that can occur faster than the speed of light. Yes, ma'am?
So if the space itself is expanding, that means the space is expanding everywhere.
That's
It means
right.
It's expanding right here. in this
That's
room.
right.
Can we measure?
Well, you'll have a hard time measuring it in this room. Woody Allen actually was worried that Brooklyn was expanding. He said that once. And it is, but not noticeably. I mean, well, I just need to give you a number here. I'll give you a number. That was given to me by a gentleman here in the front row. It's called the Hubble constant. Now you need to know what all these things are. But actually this is not even algebra. This is just a little bit of arithmetic. From this number you can figure out how fast the seats in this room are expanding due to the Hubble expansion. Or, you know, how fast, you know, your pancreas is getting bigger or whatever. Right? This is the constant of expansion. 70 kilometers per second, which is, you know, the expansion of space per megaparsec. Now, megaparsec is a million parsecs. And parsec, you know, they sometimes use that on the sci-fi shows, right, just to make it sound techy. But a parsec is about 3 light years, roughly. And if you don't know what a light year is like 5.8 trillion miles. But maybe the thing to do is say 1 parsec is about 3 times 10 to the 16 meters. So a megaparsec is 3 times 10 to the 22 meters. So for every 10 to the 22 meters, things are moving apart at 70 kilometers a second. Right? So for every 10 to the 21 meters, they're moving apart at 7 kilometers per second. For every 10 to the 20 meters, it's 0.7 kilometers per second. Work it all the way down to 1 meter. Right? Well, what is that? I mean, we can just do it. 26 to 21. It's on the order of, put it this way. It's like every second, you know, you're getting bigger by about the diameter of an electron or something like that. It's smaller than that, actually. Okay. You work it out, but it's not much. It's not something to worry about. If you're bulking up, it's probably not this. With other questions? I'm going to go through this rather quickly. I did want to get to something here that's interesting, because after all, most of this isn't. But here's some galaxies, pictures of galaxies. These galaxies are nearby. Now, these are pictures made by the Hubble Space Telescope. But what's interesting is these are galaxies, it's on vertical columns here. These are galaxies 9 billion light years away. Sorry, no, this is 14 billion. These are 5 billion light years away. And these are 9 billion light years away. And these are about 11 or 12 billion light years away. Now the point is, of course, the pictures get crummier when you're looking at things that are farther away because things are small and dim and whatever. But I think even the untrained eye, and that's probably what many of you have, can notice that these guys over here look a little different than these guys over here. Their morphology, their shape is a little different. And all you can say about these guys, yeah, they're far away, but remember, when you look at something far away, you're looking back in time, right? Because the speed of light is, after all, finite. Right? The speed of light, and this is another number for your use at parties, the speed of light is about 1 foot per nanosecond. Nanosecond is a billionth of a second. So light goes about that far every billionth of a second. That means when you look at the guy sitting next to you, right, you're not seeing them as they are now. You're seeing them as they were about 2 billionths of a second ago. Now, you can hope that they've improved in the meantime. Probably they haven't. Okay, and that's not so important, but clearly, if you look at the moon, you're seeing it as it was a second and a half ago. Probably the moon hasn't changed much either. And you look at stars, you're looking at them the way they were tens of years ago, hundreds of years ago. With your eye, you might see things thousands of years ago. But when you're looking at these galaxies, you're looking at this galaxy as it was 12 billion years ago. It's not just looking far away, it's looking back in time. Right? It's a great crystal ball. But you see, they look different. Whereas if the universe didn't have a Big Bang, the galaxies everywhere should all look the same. Right? The fact that they look different when you look back in time means that things have changed with time. And that's quite some support for the Big Bang. This is the other support. these guys standing in front of this antenna in lovely Holmdel, New Jersey, won the Nobel Prize for something they weren't even trying to do. This was back in the early 1960s. And these guys were working for Bell Labs. You may not know this, but there was a time when the phone company was all one company. Bell, right? And they were experimenting with transatlantic communication, not by using all those cables that were buried in the 19th century, but they had put up some satellites, some of these early satellites. They were just big balloons of aluminum foil. Right? They put them up there, and the idea was, well, we'll use a transmitter, we'll send your phone message up and bounce it off that balloon and then have it come back down in Europe, where we'll have a big receiver, you know, antenna, pick it up. So these guys' job was to measure the amount of background static to make sure this was going to work. So they built this big antenna, this big horn-looking thingy up here, right there in Holmdel, New Jersey. And they were making these measurements, and you know, they were measuring some static, but they noticed that there was always some static. No matter where they pointed this thing, there was a little bit of static. Too much static. They didn't quite know what it was. They figured it was bird droppings, because they knew there were birds in this thing. And they went in there, and it probably was rather unpleasant. They cleaned out all the pigeons, but the static was still there. Right? And one of them thought about this a little bit, and they said, you know, there's a guy over at Princeton, which is like 20 miles away from this place, a guy over at Princeton who's been thinking about this, and he figures that there should be some background glow to the universe, because if it really began with a Big Bang, it was a time when the universe was very hot, right, and producing lots of light, which by now had been stretched out because the universe has gotten big through the Doppler shift, and now it's not light, it's just some sort of radio waves. But this glow, which is now radio glow, ought to be everywhere. So they call that guy up. Now that guy happened to be, I happened to be a student actually at Princeton when this was happening, and my advisor, I have a name of Dave Wilkinson, my advisor was trying to measure this background glow. Now I was just a dumb sophomore, so I didn't know what was going on. All I knew was that we occasionally would see him in the back of the physics department with this antenna aimed at the sky. In fact, we didn't know what he was doing, but one day my lab buddy and I actually rolled up a transmitter, a klystron, to the window of the physics department and aimed it down at this thing, and I tapped out, "What hath God wrought in Morse code," aiming it out. We never told him, but it turned out that this discovery won the Nobel Prize, but not for my advisor, see? So I felt sort of bad about it. I told him about it years later, but he hasn't spoken to me since. But these guys, they had found it. They drove all the Princeton physicists mad because they knew what they were looking for. These guys didn't, but they found it. Serendipitous. And they found the background, and that was one of the strongest arguments for the universe to have begun at a Big Bang. Occasionally you read in the papers, Big Bang in trouble. Big Bang isn't in trouble. Details of the Big Bang may be in trouble, but the idea that there was a Big Bang is not in trouble. Right? Something you can't say for your kid brother. All right, they've actually made a map of the microwave sky. This is the whole universe as seen in radio waves. They were trying to look for these small fluctuations in the amount of cosmic static that's coming at you, and that's what this is. This was poorly called by George Smoot over at the University of California, Berkeley. I can make fun of Berkeley again. He said, "This is the fingerprint of God," which it turned out not to be a good thing to say. Anyhow, these are the slight, irregularities in this cosmic background radio radiation discovered by those other guys. They didn't have enough sensitivity to make this kind of a measurement. This took a very specialized satellite. But what it shows you is all the bumps and warts of the universe. And of course, these things have expanded now to be, 13.7 billion light years in every direction. But they were all once caused by the irregularities that existed when the Big Bang began. So this is very interesting information. Okay. I think we're going to skip it. I tell you, the really interesting thing, I don't know if any of you are getting into this, probably you're getting out of this, but if any of you get into it, the really interesting things to ask are what was happening in the first second. Because it's surprising to think that you could run this movie of the Big Bang backwards. You could run it back, you run it back 7 billion years, right? And all the galaxies are twice as close together as they are now, right? The pictures on the walls of astronomy departments will look better because all the galaxies are closer, right? But the universe won't be any fundamentally different. You could run the picture back, 12 billion years. Right now the galaxies are like 1/10 as far apart as they are now, but there's still galaxies, and the universe, the galaxies look a little different. Everything's big on the sky, but pretty much the same. You can run it back, turns out, you can run it back to a couple of 100,000 years after the Big Bang. Right now the universe is very small. The whole universe is at a temperature of like 9 or 10,000 degrees. Right? And we understand the physics of things that are 9 or 10,000 degrees. It's also very dense. Well, the physics still works. You can run it back to 1 minute. You can run it back to 1 second. You can run it back to a microsecond, a nanosecond, a femtosecond, and all the physics still works. You can run it back, well, with some difficulty, but with some credibility too. To 10 to the minus 43 seconds after the Big Bang. Now, for those of you who are not into scientific notation, this is a 0 and then 42 zeros after the decimal point. Can't write them all. 42 and then a 1 seconds after the Big Bang, and we still know what's going on. Right? Before that, if you go back to 10 to the minus 44 seconds, we don't know what's going on, because what happens when you go this far back, the universe is so small, so hot, so dense, that the uncertainty principle means you can't say anything. This is a limitation of the human brain. Right? Because, of course, the physics knew what was going on. We just don't know what was going on, right? The problem is you only have 3-pound brains. Some of you have 5-pound brains. Maybe you can address this problem. Because physicists would love to push that. Because you might say, well, that's good enough for me. I mean, gosh, there's a tiny, tiny fraction of a second, and you understand everything afterward. I don't care about that 10 to the minus 43 seconds you couldn't explain. But see, it's in that spot that, you know, the real mystery lies. What made the Big Bang? Now, the biggest discovery, I would say, the last 10 years, we've got to get to that. Dawn of time. There it is. Did you work that out? If you can, please make me a co-author. Okay. Let's talk about that either. Let me say a little bit about the future of the universe, because even though I know that the last lecture here, well, not the last lecture, there's some talk about the future of life, right? Well, the future of life depends a little bit on the future of the universe. What is the future of the universe? We've had 13.7 billion years. It's been pretty interesting. We've had stars for most of that time. Right? We've had stars that have the kind of heavy elements that produce life. Remember, in the Big Bang, at the beginning of the Big Bang, all you had was elementary particles. Right? And then, very shortly thereafter, all you had was protons and electrons and neutrons. Big super. And it's very small. It's very hot. It's like being inside an incandescent light bulb. Right? There's light everywhere. You can't see anything because the light is scattering off all those electrons. They're all free. There are no little atoms like you learned about in junior high school. It's too hot for that. But the electrons don't stay going around a nucleus. They're just wandering off. They're doing their own thing. The whole universe is this really hot, bright plasma. Okay? And for the first 3 minutes, from about 1 second after the Big Bang till about 3 minutes after the Big Bang, the temperature of all this is about a few million degrees. 10 million degrees, 1 million degrees, 20 million degrees, measured in millions of degrees. Right, so you ask the physicists, well, so you have this big plasma, as they call it, this big glob of hot stuff, a few million degrees hot, and you got protons and neutrons and electrons. Do you know anything about that? And they say, yeah, we know anything about that. That's what the inside of an H-bomb is like. And as it turns out, for very practical reasons, physicists know a lot about H-bombs. Okay? So they know what the situation is inside an H-bomb. And what happens is that you got all these protons running around. I will draw you a proton. Here's a proton magnified 400 trillion zillion times. Okay, there it is. Of course, they don't really look like this because they don't have this neatly lettered plus. The other proton. Now, there are other protons running around. I mean, this proton eventually will become a hydrogen atom, right? Because when the universe gets about 300,000 years old, it cools down, and those electrons suddenly can get into an orbit around this. So you have an electron going around it, and now, that's a hydrogen atom. And hydrogen atoms are great for, the Hindenburg and things like that. But it wasn't anything else. I mean, there's no molybdenum, no gold, no phosphor, no carbon-based life form. There's no carbon. What's that? There isn't any. Okay. But you have a lot of these protons, and they're moving fast because it's really hot. They're moving fast. They're like beetles on a skillet, right? They're moving around really fast. That isn't actually application number 1 of H-bombs, but that is what it does. Right? And they figured that in 3 minutes of the entire universe being an H-bomb, you should cook about 1/4 by mass, 1/4 of it from hydrogen into helium. Right? Now you look out and that's a very concrete prediction. This satisfies the requirement of astronomers that if you're going to have a theory about things like there was a big hot Big Bang, it's got to make a prediction I can see with my telescopes. And this is saying you should see that about 1/4 of the universe by weight is helium, and almost all the rest is hydrogen. Right? Oh, sure, stars have cooked up a little bit of stuff that you find in small amounts on planets that might turn into biology that might justify a course. But in the bulk, most of the universe is hydrogen, and 1/4 of it by weight ought to be helium. And in fact, astronomers go out and they can figure out how much stuff is out there by doing spectroscopy and other nifty things that you'll really love hearing about. And they find that the universe is about 1/4 helium by weight. There's not much helium on Earth. Helium's fairly light. It doesn't react with things, so it tends to leave. There's enough to, as I say, fill party balloons and the occasional blimp. Right? Otherwise, helium's not terribly useful, except in physics. There it is. 1/4 of the universe is this dull stuff called helium. Right? 3/4 of it is hydrogen, which might eventually power your car. Okay, that was another prediction of the Big Bang, and this is true. This is true. Okay, well, so here are the possible future scenarios. Now, let's look to the future. We've had 13.7 billion years of hydrogen atoms doing their thing, making a little bit of helium, and eventually, fusing in stars to make heavy elements, which made you. Right? You are the result of hydrogen atoms at work for 13.7 billion years. You got to give them credit, right? Or maybe not. Okay. Well, what's going to happen in the future? Well, it seemed that determining the future of the universe was really simple. All you had to do was figure out how much stuff is out there. Right? You remember those scales? You're probably too young, but they used to have scales where you put in a penny and you get your weight and fate. It wasn't just that it told you weighed 193 pounds, but it would also say, you will be unlucky in love, or something like that. So it was your weight and fate. Okay? And so they figured the same was true of the universe. If there's a lot of stuff in the universe, then the gravity of all that stuff pulling on all the other stuff will eventually cause this big expansion to slow down, come to a stop, reverse direction, and then pull everything in, and we'll be headed for a big crunch. Which would be interesting for a while, because all the things you're studying as astronomers, every night they're getting a little closer, right? It's a little better for you. Right? But of course a big crunch would be very uncomfortable. So that was one scenario, and that's a scenario here at the bottom, right, where the universe gets big. This is time, that's size. Gets big, and then it gets small again, and you get a big crunch. Some people who don't like the idea that everything ends in fire, philosophically say, yeah, but then there would be a bounce. And then you get another expansion, and then there'd be another crunch, and then another expansion, and another crunch. And this way you could have a universe forever. And people like forever. I'm surprised that the men like that, actually. But anyway. Okay, there you go. So that was one idea, closed universe that maybe even oscillates. It gets big, it gets small. Maybe it goes beyond this point, maybe not. Another possibility is that there isn't enough stuff out there to stop this expansion. Right? All the gravity in the universe is just not enough, and the universe just keeps getting bigger forever. It's called an open universe. Right? So it just keeps getting bigger and bigger and bigger and bigger. Now, one of the interesting things about the universe that's different now than it was, for example, after the first 5 minutes of the Big Bang, is that it's pretty empty. The universe is mostly empty. The average density of stuff in the universe is like 10 to the minus 29 grams per cc. That's just a number, but it's obviously a very small number. Right? Sure, there's there are higher densities in here. You have 1 gram per cc in a glass of water, but on average, the universe is pretty darn empty. Okay. Well, that's one scenario. If it's really darn empty, then maybe it'll just keep expanding. And the other possibility is that it'll expand and come to a stop, but it comes to a stop in infinite time, so you really don't want to wait. So these were the models of the universe, and people were just absolutely sure this was true. Had to be one of these three things. I mean, what else is there? Right? You got gravity working. It's either going to slow everything down enough, or it's not. Wrong. It turned out it was found to be wrong less than 10 years ago by some guys who were looking at standard candles. They were looking at galaxies very far away where they would occasionally see a star blow up in what's called a supernova. Right? Stars, big stars, when they end their lives, they blow up. That's another story for another time. But it turns out that, if their stars are all more or less about the same mass, and certain categories of stars are, when they blow up, the explosion's always about the same brightness. It's like, you have your 50 megaton bomb, and you have your 20 megaton bomb, and the brightness you get from your 20 megaton bomb is always pretty much about the same, so you can use atomic bombs as standard candles or whatever. It might be a good use for one, but these are stars blowing up, and they were looking at stars really far away because, that would tell them how fast the universe, or to what degree the universe was slowing down. Was it slowing down enough that we were going to see a big crunch, or was it not? That was the idea. And they found something incredible. Namely, that the universe wasn't slowing down at all. It was speeding up. The expansion of the universe is accelerating. In other words, you're worried about how big Brooklyn is getting every day. It's getting bigger, faster all the time. It isn't that the universe is just expanding, the galaxies are moving out at more or less a constant velocity, but they're speeding up. That's something nobody had anticipated. It's truly very, very remarkable. This is probably the biggest discovery in astronomy in the last 10 years. Now you might say, well, how can that be? I mean, you got gravity after all. Something must be pushing the universe apart. There must be something in the universe that is acting as anti-gravity. I had one of those. She was married to my uncle. Anti-gravity that must be pushing everything away. Right? And of course, we don't know what it is, so the physicists call it dark energy. It's just words, and nobody knows what it is. A lot of people have ideas, but they haven't figured it out. Okay. Right, so there are several possibilities with this expanding universe, but you might say, well, do I care whether the universe is blowing apart faster and faster all the time? Well, that's unclear whether you do. There's some theories that say as it's blowing apart faster and faster, that acceleration will in fact eventually reach down to the sizes of galaxies, and it'll cause galaxies to blow apart, and then it'll cause stars to blow apart, and then planets to blow apart, and then you to blow apart. This is something called the Big Rip, okay? And this was put forth by a guy by the name of Caldwell, who I think is at Dartmouth. Either Dartmouth or Yale, but everybody's from Yale these days. I think he's at Dartmouth. Dartmouth. Caldwell's his name. You can look him up. He talks about the Big Rip. And this is a possible scenario, and this would be a little disappointing, particularly if you have real estate investments or something, because in the end, everything just blows apart, and that's it. Even the atoms blow apart, right? That's really going to devalue your properties. Well, is it going to happen? The jury's still sort of out, but it looks like the Big Rip is something you don't have to worry about. Now, if it was going to happen, the time scale for the Big Rip is on the order of like 30 billion years from now, right? So I don't, maybe some of you don't care about that. But I mean, it is a thought. It is a thought that you might have a Big Rip. The other things that are going to happen for sure, the Big Rip probably won't happen. The other thing that's going to happen is the sun's going to run out of juice. The sun's going to run out of fuel, right? It's burning hydrogen into helium. It's got a lot of hydrogen, actually. But the problem is that it makes helium, which is kind of an ash, and that gets in the way of getting more hydrogen. Yeah, the whole life cycle of stars is a study in itself, one that's extraordinarily enervating, I would say. But we do know a lot about it, and it turns out that in another about 5.5 billion years, the sun is going to start running down. It's going to run out of fuel. And curiously, when it does that, it will swell up. When it gets old, it will swell up. In that sense, it's very much like my neighbors, actually. Okay, so when it swells up, it's going to get big. It's going to get 10 times its current size, 20 times. It'll be cooler on the outside, but because it's so big, the amount of energy it's putting out will actually go up for a while. And that means all the oceans on Earth and Palo Alto will all get, hard baked. Right? It will swallow mercury. Probably won't be upset by that. Maybe mercury isn't big in your life. It will then swallow Venus. Right, there goes the evening star and the morning star. It's gone. It might swallow the Earth. The jury's out on that. It may be that because the sun also throws off some gas and becomes a little less massive, the Earth will actually move farther out and will be spared getting swallowed, but we will not get spared having all the oceans boil away and, it's going to be really uncomfy. Right? But this is just a short-term problem. Right? We can beat this rap. The way you can beat this rap by just going to another star. No problem. Right? And you might say, yeah, but go to another star. We can't do that. No, you can't do that now. But if you got 5.5 billion years to solve this problem, and the incentive that if you don't, you're going to get baked, you may solve the problem. So I'm not so worried about this. I think you can beat that. It's like global warming. Everybody's worried about global warming. You can actually beat that rap. I mean, clearly there are various things you can do. The trouble is that in the future of the universe, there are some things where it's not clear there are things you can do anymore. Okay? All right. Then the sun collapses down to essentially a charcoal briquette. And in fact, according to some models, the center part of this charcoal briquette is so condensed that the carbon atoms actually are lined in a crystalline lattice and becomes a big diamond. Now, some stars have already done this, and maybe this is a mining opportunity for somebody. Imagine a diamond the size of well, it's got the size of the Earth, but it has the mass of the sun there. It's a lot of diamond pleasure. Good for lives. Okay. So that's the future of the sun. It's going to turn into charcoal briquette, but it takes a long time for this to happen, for it to finally cool down to the point where you're not getting any light out of it. That time for that is on the order of 100 billion years, more or less. 100 billion years plus or minus a week or two. So that's the future of the sun. Now, not so bad for us because we just move, right? But the problem is that the universe is not recycling, and so all the stars are going to end up either as charcoal briquettes or something else terrible. All the stars are going to go out. After that, terrible things happen. They continue to happen. The universe keeps expanding, and it never, you never get the big crunch. The universe goes on forever. And the terrible sorts of things that happen, we'll run out of time here, so I won't go into too much detail. But, things like collisions begin to make a big difference. Right? You don't worry much about the sun running into another star. The chances of that happening are tiny, really tiny. In the whole history of the galaxy, a star at the position of the sun, maybe one star in a couple of 100 billion may have come close to another star. It just doesn't happen. Right? It's like having the whole freeway to yourself, right? Just not going to happen. I mean, you got a ping pong ball here, that's the sun. And the next nearest star is another ping pong ball in Salt Lake City. What are the chances that those two ping pong balls are going to collide? Never happen. Well, never is not quite right. If I give you an infinitely long time for things to happen, everything's going to happen. That can happen. And in fact, it's clear that slowly, you get these collisions, and you get a collision. It's just, they don't actually hit one another, but they get close to one another. And one of them gets sped up and tossed out of the galaxy, and the other one gets slowed down and goes to the center of the galaxy and becomes part of a giant black hole. So if you look at the galaxies, maybe 10 to the 50 years from now, that's a big number, but 10 to 50 years from now, there'd just be these big central black holes and all these charcoal briquettes, sort of like a swarm of gnats around it. And it's going to be hard to have a good life at that point. But things still happen. Things still happen up until this date. Mark it on your calendars. 10 to the 100 years from last Tuesday. Okay? That's, that's 1 followed by 100 zeros. That's a long time. That's a long number of years. You probably won't see that in your lifetime. But at that point, physicists can tell you the last thing has happened. After that, the universe has become so big, so cold, so diffuse, nothing more happens. There isn't enough energy. There's no energy sources in the universe that allow you to roast a marshmallow. It's kind of the end of time. It isn't that time actually stops, but nothing more happens. Nothing ever happens anymore. So here's the bottom line, and we'll just end right here. You may remember back in junior high school, right? Maybe you made one of those timelines, right? The history of the Earth. Right? Earth forms 4.5 billion years ago, right? And then, after about 1 billion years, you get life, and then you get, some multicellular life, and then you get the Cambrian explosion. I guess that's more or less the same time. And then you get, trilobites, always interesting, good conversationalists. Then you get the dinosaurs, right? And then the dinosaurs get wiped out 65 million years ago. And then you get the first, the last inch, human history, whatever. You made these things, right? They go all the way around the room. All right, now consider the future. You got to keep going around the room, maybe another same amount of distance around the room, and now the sun is beginning to die. And then you just keep going around and around. And the point is that the future of the universe, you never come to the end of it. You just got to keep going around and around, not for a long time, but forever. So there's the history of the universe. Big Bang, 14 billion years ago. There'll be about on the order of 100 billion years of excitement, in which there's stars, planets, and stuff like this. Right? And then everything begins to die, but it doesn't stop. It just keeps going forever. The history of the universe, bam, a little flash of something, and then an infinite amount of time of nothing. And that's it. So I think it's a sort of an upbeat story. I'm glad I could present it to you today. If you have any questions, you can come see me.
I feel like not even having anyone else lecture this semester. Seth, that was absolutely amazing. Thank you so much. Thursday, I said Greg Laughlin's coming. Now, one of the cool things that he's been doing is working on some computer models to look at orbits around stars. And I know he was really excited. There was a new one that came out like the week after he lectured last year. But he told me that he was really excited to try some of his new ones on you guys. So if you have a PowerBook, you might bring it, because I know his stuff is web-based. He might want, I was just emailing to try to get a response. He might want you to try to follow along just because he'd like your feedback. So if you'd like to do that, you're welcome to. Now, probably many of you are thinking, what do I need to know about all this great stuff? Well, as I mentioned at the beginning, you need to be able to stay current. You need to know how to do that. You need to have some facts in your gray matter. My favorite student evaluation said this class is great for cocktail parties. Seth's given you lots of great information to impress people of the opposite sex or not at parties, so that's great. And I want you to get what you want to out of it, the cool stuff. So to help you make this enjoyable, you're going to have the taping from iTunes, which is a great improvement over the past. So you'll be able to listen to it again if you want. You can really enjoy the lectures. We always, if the professors allow us to, put their slides up on coursework. And I've already sent Vichy mine from today. I'm sure we can get Seth's and so on. So you can go back and look at the original PowerPoint slides. They say we'll be giving you chapters in the book. And there'll be some people who will recommend extra reading if you wish, or they will say you need to do this by the next class. So all that will be on coursework. Don't angst, get everything that you can out of it, and I think you'll enjoy the class. And I'll see you, hopefully everyone, on Thursday.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.